Hey, this is Mr. Ayton. Welcome to the 2024 AP Chemistry exam that was just given a few days ago in May 2024. This is free response question number 1. Let's get to the answers. This is kind of an acid-base reaction between lactic acid C3H6O3 and a strong base sodium hydroxide. According to the balance reaction above, it's not the net ionic, but it is the balance reaction. And the first thing they wanted us to do is circle the hydrogen atom that most readily participates in the chemical reaction. Since it's an acid, a bronzed acid, it's going to donate the H+, which means the H+ right on the end is going to get donated to become a conjugate base. Part B says the student begins the experiment by dissolving 10.22 grams of sodium hydroxide. What do we always do with grams? We divide by the molar mass. They gave us the molar mass. That gives us the moles of sodium hydroxide. Then we take those moles and we divide by the number of liters, 0.500 liters, and we get 0.511 molar of sodium hydroxide. Part C goes to the titration of that lactic acid using a burette, a pH meter, and the 100 ml Erlenmeyer flask, and we're titrating the lactic acid. You can see the lactic acid, the equivalence point is at 16 milliliters of the sodium hydroxide being added, and they want to know the pKa. Well, the pH is equal to the pKa when we're halfway to the equivalence point. So if the equivalence point is at 16 milliliters of volume of NaOH added, we're going to go to 8 milliliters and take a look at 8 milliliters. The pH is approximately 3.8. Therefore, the pKa is 3.8. Then it says part D, we have a part on this titration curve where we have a buffer. We have some acid, that weak acid of HA, that's the C3H6O3, and we have the conjugate base, the A-, the C3H5O3-. And take a look at our particle diagram. We have 4 moles of the HA for every 2 moles of the A-. That's a 2-to-4 ratio of the A- to the HA. And so we plug that into Henderson-Hasselbalch, not Hasselhoff. That's David Hasselhoff. But Henderson-Hasselbalch equation, that's pH equals pK plus the log of the A- over the HA. Our pK was 3.8 plus the log of 2 over 4, which gives us a pH of 3.5. That's D2. That's justifying your answer. So we got to go back to D1, and we got to put in X right at about 3.5, which is before halfway to the equivalence point, about 5 milliliters added on that titration curve. Then it goes to problem 3 for part D, and the student repeats the experiment but uses a double the sodium hydroxide concentration, which means the NaOH concentration is at 1 molar, 1.0 molar. It used to be at 0.5 molar approximately. And if you did M1V1 equals M2V2, what you found was you needed half as much of the NaOH. Therefore, the titration curve would still start at the same point at just above 2. It's going to hit the equivalence point at 8 milliliters of added, and then it goes up. This is kind of a rough picture of what your titration curve would be graphed. Then we go to part E. Part E, in a third experiment, the student is investigating the enthalpy of the reaction. Therefore, now we're in a thermodynamics problem, a thermochemistry problem. And you can see they took 100 milliliters of the 0.5 molar lactic acid with 100 milliliters of the 0.5 molar of the NaOH. They put it together, which means you have 200 total milliliters. If we know the density of water is 1 gram for every 1 milliliter, we know we have a total of 200 grams of the solution. Well, the solution also has a specific heat of 4.2 joules per gram degree Celsius, and the solution changed from 20 degrees Celsius up to 23.2. So we calculate for significant digits, 2690 joules of heat that the solution absorbed. That's the surroundings. The surroundings absorbed that. Therefore, the reaction was giving off heat. The reaction was exothermic. So part 2, we take the limiting reactant. We have to take a look at the limiting reactant. You see the lactic acid, there's 0.500 molar of 100 mils, and the NaOH, 0.500 molar of NaOH of 100 mils. Only one of those is the limiting reactant. So we take one of those, 0.5 molar times 0.1 liters, that's 0.0500 moles. That is the limiting reactant that was used. So we take our heat from part 1, that 2690 joules, we change that 2.690 kilojoules. We divide by the limiting reactant's number of moles, and we get 53.8 kilojoules per mole, but it's negative because The temperature went up, therefore the reaction was an exothermic reaction. You got to have that negative. They're probably going to give you a point for that sign in your answer. Part 3, the student claims that if heat was lost from the calorimeter to the surrounding air, which means we're losing more of that Q, more of that heat, what happens to that molar enthalpy? The student thinks it's going to be smaller. I agree, it will be smaller because the heat was lost due to the surroundings in the air. Less heat in joules would be in the molar enthalpy calculation. That's the numerator. The same number of moles reacted. You're still using a limiting reactant. Therefore, the molar enthalpy of the reaction would be smaller in magnitude. And that is the full 2024 AP Chemistry exam. Free response question number 1. Take a look at my answers for all the rest of the questions on my YouTube channel. Thanks, guys. This is Mr. Ayton signing off.